Thank you. Okay, thank you very much for being here, and thanks a lot to the organizers for inviting me. It's a great pleasure to come back to Galileo Galilei Institute. So as you can see from my title today, I'm going to be talking about the entanglement content of particle excitations. I'm going to this is going to be a rather basic talk, so I'm going to try and explain everything quite carefully, at least what we are computing. I won't have time to give you a lot of the technical details, but I will indicate what they are. So this is work that is based essentially on two papers. One of them is already on the archive. It's a letter. It's relatively short. And there is a longer, more technical paper that we are working on, and it should appear very soon. And I should start the talk also by thanking all my collaborators, and I'm very pleased to say they're all here today, which is very nice. So it's Benjamin Doyon, Cecilia De Fazio, who is now a PhD student of mine, and Ishwan Seceni, who is a postdoc in our group. So what is this about, quasi-particle excitation? So this is about entanglement of excited states. Obviously, this is not the first work on that topic, but I think the kind of excited states we're looking at are relatively new, and we have some interesting results for that. So let me describe from the beginning what we are computing. So the setup is one you will be very familiar with if you ever heard any talks about entanglement. And I think some of these formula you're going to see many, many times in this conference. So I'm pleased to be the first one to show them. So in our work, we have been looking at a very simple configuration, the simplest bipartition you can think of. We have a periodic system. You can think of it as a periodic spin chain, although our computations really are in quantum field theory, so the scaling limit of this system. And we have a bipartition like that. So we have a region of length L, and we have the rest of length L minus L, little l. And for the moment, this is going to be in one dimension, in one space dimension. A little bit later, I'm going to show you that actually our results apply also to systems in higher dimensions. But the original computation we did was really for free theories in 1D. So we're going to start with that. And we're going to look at a system at 0 temperature, so it's going to be on a pure state to start with, so the simplest configuration. I'm going to show you the definitions of a couple of quantities you will be familiar with. So the things we're going to be computing are entanglement entropies, and essentially we looked at three variants of this quantity. We looked at the Renyi entropies associated to a state phi, which are defined in this way, and this is the reduced density matrix in the usual way. And what's special about this definition is that this state phi, in my talk, is going to be a particular type of excited state in quantum field theory. And I'm going to be dealing also with massive quantum field theory, so this is going to be gapped systems. Okay? Now, there are certain limits of these Renyi entropies you will be familiar with, probably, which is that when you take n to 1, you get the well-known von Neumann entropy, or bipartite entanglement entropy, and if you take the limit to infinity, you get something which is called single copy entropies, which maybe you are less familiar with, but it's also a measure of entanglement. And I'm going to indicate these quantities by a 1 here and an infinite there, meaning the limits, the corresponding limits. Okay? So these three quantities are going to appear many times, and a priori they will be functions of these two length scales in here, the size of subsystem A and the whole size of the full system. Okay, so what are we looking at specifically? So we want to look at excited states which have 0 particle density. So we actually have a finite number of excitations. Now, these kinds of states are very natural to look at in one-dimensional quantum field theory because there is a natural way to describe them. So my background personally comes from integrable systems, integral quantum field theory, and in there we always describe states in terms of the momenta of the particles or their rapidities. So what I'm going to be talking about are states where we have, in general, k excitations, okay? And this k is a finite number. It may be 1, it may be bigger, but it is finite. So this is a zero density state, and it's important to say that, but because a lot of works about excited states deal with finite density, so very highly excited states. That's a little bit different, and the behaviors you observe there are a little bit different too. So, okay, we have those states, and in the computation that we did originally, and I'll tell you a little bit about the technicalities of that later, what we looked at specifically are the simplest massive QFTs you can think of, which are massive boson or a massive fermion. So we looked at those because they are the simplest, and even in those simple cases, actually the analytic computation leading to the results I'm going to show you is rather non-trivial. Later on, after we found the results and we realized they were really simple, we realized that they had a more general interpretation and that they could apply to more general systems, including in higher dimensions. So I'll come to that as well. An interesting feature of our results is that, in particular, so for free fermions, this kind of state, generic state I'm presenting there, is required to have a set of different momenta. So the momenta of the particle must be distinct because of fermionic statistics. But if you have free bosons, you may have momenta or rapidities that are repeated. And what we found is that our result actually depends on that, fundamentally, on whether you have distinct or non-distinct rapidities. Of course, I should mention that many other people have worked on excited states. I'm going to mention just 3 works in here, and I apologize if any of you have done things I haven't mentioned. But there are 3 extensive studies of excited states which have been inspirational for us. One, probably the best known and the oldest one, perhaps, is the work of Alcaraz, Berganza, and Sierra from a few years ago, where they looked at the low-lying excitations in conformal field theory. We're looking at something similar, but now in a massive theory. There's also very extensive work by Vincenzo, Maurizio, and Pasquale, where they looked at excited states in critical XY and XXZ chains, and this is a very big study of those cases. But in this work, they were looking at highly excited states, so slightly, it was also critical, but also the type of states they were interested in was a bit different. And finally, there's this work by Vincenzo and collaborators where they looked at gapped XXZ chain, and because this is gapped, this has a slight closer connection to what we did, and I'll mention it later where the connection appears. So let me then tell you more precisely what we compute. So what we compute is not just the entanglement of those excited states, but rather something that in the work of Hermann Sierra and collaborators, they call this the excess entanglement. So the difference between the entanglement entropy in the excited state and in the ground state. So we look at an increment of entanglement. And we look at it in the scaling limit in QFT, in a particular scaling limit, which is the limit where the size of the system and the size of the region are both infinitely large, but the ratio is kept fixed. And it's finite. So this ratio, this little r, is going to appear many times, and it's a number between 0 and 1. Okay? And it's important that it's kept finite. If you take L very small, so if you take this little r to 0, actually our results, they give 0. They become trivial. So the fact we see something non-trivial has to do with keeping this ratio fixed and finite. And this is the sort of thing we'll be looking at. So I call it delta because it's an increment. So it's the difference between entanglement in excited state and entanglement in the ground state, indicated by this 0 here. And the interesting result we have found is that if we look at this particular limit, when the size of the system goes to infinity, this ratio is kept fixed, and we looked at this difference of entanglements, then the result is a very simple function that depends just on this ratio r, in this parameter r, in a very, very simple way. So simple that actually it doesn't really depend explicitly, for example, on the momenta or energies of the state, which is slightly surprising. Okay, but in this limit, when L goes to infinity, actually the momenta don't matter. It just matters whether some of them are distinct or equal, but their values actually don't matter for the result. So let me show you the results. So I'm going to start with the simplest situation, which is one single excitation. Okay, so we have a state, one single excitation, one single momentum, and we look at the increment of the Renyi entropies. And the other entropies I defined earlier. And this is the formula that you get. So you find that the Renyi entropy of one excitation is a function that looks just like this, where this r here is that ratio I was showing you. And if you take the limit when n goes to 1, you get von Neumann, which is the usual familiar expression for many of you, probably. And if you take the limit when n goes to infinity, you get this function here, which is the increment of single copy entropies. It's a function that has a cusp, actually at r equals a half. Okay? I can show you a picture of that. So these functions, they look like this. They all have a maximum exactly at log 2. So you can say that the amount by which entanglement is increased by the presence of the excitation is at most log of 2, which is quite natural for one particle. And what you see here is that the outermost function, this is the von Neumann entropy, and the innermost function here is the single copy entropy that has this cusp. And then in between, we have all those Renyi entropies with different values of n. Okay? We didn't take n less than 1. We didn't look at that case. But yeah, that's also interesting. So the fact that there should be a maximum at log 2 was suggested, predicted, found in other works before. And in the work of Vincenzo and others, this formula actually was also proposed to be a semi-classical limit. Because this formula, I mean, some of you will recognize this is really very simple. Might recognize that this is just, yeah? This is actually both fermionic and bosonic. We get the same result, both for bosons and fermions. And one thing that we realized after we got this result is that this is, if you look at this formula as representing the entanglement of a state, it turns out that this simple 2-qubit state exactly has that entanglement. So in a sense, the formula is telling us that when we have one excitation, essentially the only thing that matters is whether this excitation is localized in the region A or in the rest. And you can describe the same entanglement by a state like this, where you have a single particle and you have probability R to find it in region A and probability 1 minus R to find it in the rest of the system. Okay, so the entanglement is giving you some fundamental information about the presence of one localized excitation, and it doesn't care about anything else. It's not telling you details about the momentum or other properties. This might be surprising, but those details, this dependency on the momentum and other properties, they will arise if you consider finite volume corrections to this result. Okay, and we have also looked a little bit at those, but in the limit when volume is infinite, the only thing that survives is this. Now, as I said in previous works, and I think probably this was known to many people, this has often been described as the semi-classical limit of entanglement, semi-classical interpretation.
So is the volume tending to infinity and the mass fixed, or the mass is also going to 0?
No, the mass is fixed, so there is a gap. The mass is fixed, but because you take the difference, because this is a difference, the dependency on the mass drops. So the mass, when you subtract the ground state entanglement, you subtract the mass as well, but it is in there.
So it's kind of a limit of large mass. If you think a fixed circle is a limit of large mass, is the same?
I mean, I don't think we take any limit on the mass. I mean, mass is finite, so it certainly is important that the system is gapped, but it's not necessary that the mass be large. It's just that somehow when you subtract the ground state entanglement, you subtract this saturation, this dependency on the correlation length, but it is still there. Okay, so what was surprising to us when we got this is that it's very simple, but also this actually emerges from a rather technical computation in QFT. So this is an analytical result, doing a calculation in quantum field theory and using, well, the properties of the QFT. So that we in the end arrived to that was quite surprising to us. So this is one excitation, and you might ask, what about more complicated states? So you get similarly simple results. So if you look at a state which I indicate like this, where you have k particles, but they all have distinct rapidities or distinct momenta, both for fermions or for bosons, what you find is exactly k times the previous result. Okay, so I can show you the formulae. They're exactly the same formulae, but if you have k excitations, you now have a factor k. Okay, so they just add up. And again, you don't see dependency on the momenta. It doesn't depend whether these particles have wildly different momenta or quite close. It only depends on how many of there are and whether they are equal or not. And I mean, here's a picture. It looks exactly like the same function, but if you have 3 of these, for example, now the maximum of entanglement is at 3 times log 2 rather than log 2. You can also have a qubit interpretation, of course, of this entanglement. You can think of it as the entanglement of a very simple state. But now this is a state that looks, well, less simple than before. You now have kind of 6 qubits, and they're telling you about whether where these 3 particles are localized. So you have, for example, the 3 of them in region A, each of them with probability R, or the 3 of them in region B, each of them with probability 1 minus R, and all the mixed states and their permutations. Okay, so you can always find a representation like this. So it looks a lot like before. Something that's a bit more interesting is what happens if you have a state where all the rapidities are equal. So this is only allowed for bosons, okay? So that arises in a free boson calculation. In that case, the particles are undistinguishable. They all have the same momenta. And this reflects in the features of entanglement. So what you see is that now there is going to be a function like this that's going to enter in all the formulae. And this function here, actually, what it's measuring is the probability of finding Q out of these K particles in region A, and the rest in region B. That's all. And that probability now is weighted by this binomial here because all these excitations are undistinguishable. That's the only difference. And what you find is, well, the equivalent formulae. So you have the Renyi entropies, now depend on powers of this function. You have the von Neumann entropy, the limit n to 1. And you have the single copy entropies. And these single copy entropies now, they develop lots of cusps. They don't just have a single cusp in the middle at R half, but now they actually have K cusps, where K is the number of excitations. So I can show you a picture here with 3. So if you have, for example, 3 excitations, all of them of the same momentum, this is the sort of functions you find. So the outermost is the von Neumann entropy, the biggest. The innermost is the single copy, so it now has these 3 nice cusps. And then in between, you have all the Renyi entropies that kind of flow between small n and larger n in this way. Okay, so you get lots of nice pictures. And you also have a qubit interpretation of this state. You could get the same entropy just by writing a state like this, where you have either the three particles in one region, the 3 particles in the other region, 2 in one, and 1 in the other, and vice versa. And now these 3 here comes from this binomial coefficient that is counting the fact that they are undistinguishable. So although all these results are very simple, it is nice there is a difference between distinguishable and undistinguishable excitations, because it tells you that this result really knows about the statistic of the particles. And this is rather nice to be able to get this analytically. Okay? So these are the results we got. And then you can think of more general states. Well, what about a mixed state where some rapidities are equal and some are distinct? Well, you can probably imagine what's going to happen. Essentially, you get combinations of these results. So if you have a mixed state, and you have something like that, where you have ki particles of a certain rapidity, and all the rest of a different one, or momentum, if you want, the formula you get are just the sums over the formulae that I showed you earlier. Okay, so you get any combination you like. Here I have some pictures just to show you what happens. For example, the picture in the middle will correspond to the entanglement entropies of a state where you have 5 particles, 2 of which have the same momentum and 3 others with a different momentum. So you just add up the formulae, and again, you will have a qubit interpretation, and okay, similar simple formulas. Yes? A volume, so, I mean, the result is what I show you. Is this volume law? I mean, volume law usually is found when you have finite density states, I think. So here we have 0 density states, so it's a little bit different.
No, I think the question is just if you take your R, these are 3 parts, you can take R to be of the order of L, and maybe you find a volume law. I don't think it's forbidden, the formula should be valid.
Yes. Yeah.
Even if they become many, the formula should work.
Yeah.
No, but this is the limit is taken with 5 number of particles there. So you always have 0 density too.
I don't know if the
Particles are finite. Take it infinite and see.
So R can only be, I mean, here is between 0 and 1. So, yeah. So I don't know.
R remain between 0 and 1. The number of particles become expensive.
Possibly, I mean, I don't know. I don't know. So if I mean, I understand what you mean. If you make the number of particles very large, does this approach a volume law? I think that perhaps in our calculation there is an assumption of a finite number of excitations somewhere. So I think if you make that infinite, there will be some subtleties that we are missing.
But for an infinite number of particles, because of the ETH hypothesis, you should get a volume law.
Yes, but what I'm saying is that that's true. But what I'm saying is that the computation that we did intrinsically assumes a finite number of excitations. I don't know if it's hard. I mean, we didn't try to do that limit, but maybe it can be done. But I think technically, in the computation we did, it is important to assume the number of excitation is finite to describe the state in the way we did. Okay, so I'll have I'll think about it. Perhaps it's simple.
I mean, the result is already for infinite volume, right? So you won't see the volume of the cell. But fully increase the number of particles, you should.
Could be some crossover. Could be more complicated. Either formula.
Probably. Okay.
Just to make sure you keep this momenta finite.
Yes, the momenta are finite. Yes. Yeah.
Do you take the momenta immediately and take your scaling grid to the
Maybe. Okay, but that's yet another limit. Yeah. So probably you could use the same techniques and take that limit in that way, but that's not what we did. Yeah. Okay. Other things? Okay. So this is the results. All right. So very simple, easy to understand. Now, so what can we do with that? Well, when we got these results, we were surprised they were that simple. So we wanted to have some numerical verification of them. So we did some numerics to check that indeed you get this formally. And the numerics that we did, we call this, or the method we use, we call it the wave functional method. So it's a numerical and exact diagonalization method for a system, the harmonic chain, which is supposed to be a discrete version of a free boson, a massive free boson. So we looked at the boson in this case. And in the harmonic chain, there is a discrete system. It has a dispersion relation that is non-relativistic a priori, but you expect that, so delta x is the lattice spacing here, p is the momentum. You expect that if p delta x over 2 is rather small, this should reproduce the quantum field theory behavior. So this should be the QFT regime, if you wish, which is the regime we prop in our calculation. So we expected to recover our results in this regime. And here we have an example. I'm going to show you an example where everything works very, very well. So in this example, I have 3 curves and a set of 3 sets of points as well. The agreement is perfect. The curves come from the formula I showed you earlier. And this is the example of this is an example of Renyi 2. This is the Renyi 2 entropy of a 3-particle state for the 3 possible cases you can have. So you can have 3 distinct momenta. That's the top curve. You can have 2 equal momentum, 1 different. That's the middle. Or you can have 3 particles of exactly the same momentum. That's the lower curve. So you have these 3 cases. And you see that, and you do a simulation on a harmonic chain of this situation, and you find very good agreement. In this case, lattice spacing is this value. The length of the chain is 10. The mass was 1, so correlation length is 1. And the momenta, they were chosen always between 10 and 50. So essentially, this is in this regime, what you call the QFT regime. Everything works. What is interesting is that although our calculation is QFT, actually, these results seem to work much more widely in other regimes as well. So here's another example. These are the entropies, the Renyi entropies of a single excitation. Okay, so these are different ends. And you can hardly see it, but there are lots of curves in here, which are the analytic curves, and then lots of dots on top, which are perfect match. And this is also a numerical simulation where now instead we took the momentum of this excitation to be rather large, 100 pi, this value. Delta x is still 0.01. The length of the system is a bit smaller. The mass is still 1. And what's interesting in this example is that this quantity, 2 pi over p, is of the order of the lattice spacing. So this 2 pi over p, you can think of this as the de Broglie wavelength of this particle, if you wish. And the fact that this is of the same order as the lattice spacing means that we are probing now really the discrete regime, the non-universal regime of the system. So this is not QFT anymore. This is a situation where the particle is really seeing the lattice structure. And yet, the agreement is still extremely good. So these formulae work a little bit further than our calculation indicates. In fact, when we thought, we explored this quite a lot, and we did many simulations. What we actually concluded is that, in general, what matters is the relationship between the various length scales in the problem. Okay, and there are quite a few of them, because the lattice spacing and many other things. But essentially, there are sort of like 2 correlation lengths almost. There is the correlation length of the system, but there are also the de Broglie wavelengths of all these excitations in there. And then we have the size of the subsystems, the 2 of them. And essentially, what you find is that the formulae seem to work whenever this inequality is satisfied. So, roughly speaking, whenever a localized particle picture is reasonable, in any situation where a localized particle picture is reasonable, you find this kind of result. because this result is kind of counting excitations in a way, counting whether the particle is in region A or is on the rest. Okay, so this is quite nice. This applies in various regimes. Another thing that we thought of after having all of these results is that if you think about this qubit interpretation of the formulae that was so simple, and which I'm repeating many times, we are saying this formula are telling you about where the particle is localized. And if that's the information that they give, then actually there's no reason why they should only work in one-dimensional systems. Why not in higher dimensions, if this is what they are telling us about? So we wanted to test if this hypothesis was true, and we did some simulations in 2 dimensions in the harmonic lattice. So what we suspect, and this is our proposal, is that actually this formula holds in any space dimension, at least for free theories. If there's particle production, we're not entirely sure what happens, because if there's particle production, there may be other interactions playing a role. But at least in free theories, we expect that essentially if we replace this parameter R by the ratio of the d-dimensional volume, so volume of region A divided by volume of the whole system, that we would still have exactly the same formulae. Okay, that was our hypothesis. And this hypothesis is supported by a couple of results or a couple of ideas. One idea that supports this hypothesis is a technique which is called dimensional reduction. I mentioned here this paper because in here they use this technique in a different context, but I'm sure the idea is not original from them. And the idea of dimensional reduction is that I'm going to illustrate it with a picture. I think it's easier to see. So suppose you have a 2-dimensional system now, and these are the regions A and B. Now, if you are growing the region A in the way I show here, so essentially you are growing region A by only growing really one of its dimensions, whereas the other dimension was already maximal all the time, then in effect, this is a one-dimensional problem still. You have a 2-dimensional system, but the parameter that's changing is just one of the dimensions. And in that situation, it's very easy to show that the same results should apply. And this can be shown not just numerically, but really from the quantum field theory point of view. At least for free theories, you can argue that essentially you have a one-dimensional boson in that dimension. So at least in sort of fake high-dimensional problems, where only one dimension is involved, we expect things to work. But what is nice is that this also works when you have really not a quasi-one-dimensional problem. So I'm going to show you some numerical results on a harmonic lattice. And you will see that they still agree very well, even though in that case, dimensional reduction does not apply. So let me show you a couple of curves that look just as before. So these are results for harmonic lattice. And it's very hard to see, but on top of each of these curves, there are 2 sets of points, 2 sets of values. So this is done for a toric lattice with, which is 50 by 50, so it's a square lattice. The lattice spacing here was 1, okay? And we have, and what we represent here is actually the Renyi 2 entropies for a 2-particle state. So essentially, the upper curve is a 2-particle state with 2 distinct momenta, and the lower curve is a 2-particle state with equal momenta. Okay, the entropy is always a bit smaller. And we have 2 sets of points. So one set of values corresponds to mass 1 and small momenta, and the other set of values, the crosses, which are inside the squares exactly, they are small mass and large momenta. So they're kind of these 2 regimes, the QFT and the non-universal regime. And you see that they both fit perfectly with the analytical curves. The way we grew the region for this example numerically was like this. So actually both the whole system and the region A, they're both squares, and A grows as a square, which means that in particular, when you get to this configuration where R is a half, which is the maximum of these curves, the system is not symmetric now. In 1D it would be symmetric, so they both really look the same. But here it's not. A and B are quite different, and it's still the same symmetric curves. Functions of R and 1 minus R emerge exactly as before. Okay, so this works very well also in this high-dimensional case, which is nice. Okay, so we have those results. Other things I have mentioned earlier and that you can explore are the finite volume corrections. So these are results for the limit when the volume is infinite. But if you do a QFT calculation in 1 dimensions at least, which is what we know how to do, you can also access finite volume corrections. And that's something we have studied a little bit want to study more in future, but I want to show you at least some results. So this is some numerical results for harmonic chain and for the harmonic lattice. Okay, so it's 1D and 2D. We see similar behaviors. And what I'm plotting here is the maximum value. So I'm looking at this point right at the middle of the curve. Okay, the maximum value of the Renyi 2 entropy of a single excitation in this case. So it's a single particle state, Renyi 2. I look at the middle of the curve. The value there is exactly log 2. I subtract that value, and I plot this in a log-log scale, essentially. So for finite volume, I should see that when volume is large enough, I expect to have essentially 1 over L corrections to the result I showed you earlier. So to this log 2 that's already subtracted. And this is what we see. So you see that you have a bunch of points, and eventually they'll coalesce around a line. And then you can try numerically to fit the slope of that line. And we have done this here for these two curves. So for the harmonic chain, we get a value such as this. And actually, from the numerics that we did, this looks very much like a power 2. So it looks like the correction goes like 1 over L squared. Okay, so it's a negative correction. We approach log 2 from below. Log 2 is the maximum. And then we have a correction that goes like 1 over L squared with some coefficient. For the harmonic lattice, there seems to be also an algebraic correction, 1 over L to some power, which doesn't seem to be an integer. But we still have to examine in a little bit more detail what this power is. When I presented this talk 3 weeks ago in Vienna, actually, people asked me, and that's a good point, were saying, but do you see any effects of the shape of the region? Because people like Eric and many others have studied systems in high dimensions, and they've written papers about how, for example, the presence of corners in a certain region affects the entanglement. Now, from their results, from what they have told us, the way that affects entanglement is contained actually in the part we are subtracting, because remember here we are subtracting the entanglement of ground state. So perhaps we don't see those corners at all. We haven't explored many shapes, but we didn't seem to see that effect. But one hypothesis we have is that perhaps this power in here, that's such a strange number that doesn't seem to be an integer, perhaps this power knows something about the shape of the region, and that's something we'd like to explore a little more in future, numerically at least. But still to be done. We don't know. Okay, what we can say at least is that there are definitely algebraic corrections in 1 over L, as you would expect, both in 1 and 2 dimensions. And in 1 dimension, we can hope to compute those analytically from the techniques I'm going to tell you about. So what's the time now? Okay, so, okay, any questions about this till this point? Yes? No? Yeah?
Well, I don't know if you were going to talk about this, but can you give us any intuition for why it's negative?
For why it's negative? Well, the intuition somehow is that, my intuition at least. So you see that, at least if you look at this curve, which is the case of two distinct momenta, you see that all these curves, they seem to tell you that for every excitation that is in there, this excitation contributes log 2 at most to the entropy. And that's kind of natural for particles. So log 2 is the maximum entanglement you can add. Since this is the maximum entanglement you can add, you would expect that if there are corrections to that, they will diminish rather than increase the entanglement. That's the idea. And that's what people find, not only us, but actually in the work of Vincenzo in quantum spin chains, they also find this, that they approach this formula that we get, they approach then in the large volume limit, and then on the way there, they see negative corrections, again, to von Neumann in that case. So that's the intuition somehow. Other? I don't know. I mean, so Fermi liquid. This is critical. Yeah, it's a critical system. So, I mean, the fact that there is a mass scale is rather important for these results. So the equivalent set of results for critical system, I think that's essentially what Germán Sierra and collaborators obtained in the work I mentioned at the beginning. So they look at critical systems, low-lying excitations in critical systems, and they look at the difference of entanglements in that case. And they also find an expression which is dependent on this ratio R, okay, with some power. But the dependency is quite different looking from ours. Okay, so they have, I don't remember exactly, but I think they have R to some power, which is actually the conformal dimension of some field in the CFT. That I don't know. I think they look at just 1D CFT. I don't know if anyone has generalized it. Yeah, okay. So in the few microseconds that are left, I'll tell you about the techniques, okay, a little bit, very summarized. So when you look at these results, they look really very simple, and somehow intuitively, once you have seen them, you say, okay, yeah, it makes sense intuitively, yeah, it counts excitations and so on. When we obtained them, we went at its brute force, so we said we're going to use QFT techniques to get this, and we had no idea about the result. Actually, we didn't think about it until we got it, and then we're surprised by how simple it was, and then understood the interpretation. So if you do the calculation using QFT techniques in one dimension, this is quite involved, but there are essentially, the ideas are easy to understand. So let me tell you the basic idea. So there are two techniques that we used. And if you know our previous work, you won't be surprised by what they are. So the first thing we used is what we call this branch point twist field technique in massive theories. It's something we developed a few years ago. And this is a way to express measures of entanglement in quantum field theory as correlators of a certain kind of field, a local quantum field. And in particular, so unfortunately I don't have time to tell you the details about how this field comes about. I'll tell you a little bit. But in terms of these branch point twist fields, the sort of thing I'm computing here for you, or the formulae that you have seen, they come from evaluating a ratio of 2-point functions. Okay, so you have 2-point functions of these fields for an excited state phi divided by 2-point function for the ground state. Okay, so this is what you have to compute. You compute this in finite volume, you take the volume to infinity, and the results that you get is what I show you. This is what we did. Okay, so this is technically relatively involved for various reasons. These two fields are Hermitian conjugate to each other. They are symmetry fields in a so-called replica theory. So a theory consisting of n copies of your free fermion or free boson. And those n copies are this n in here, the n of Renyi entropy. And then this computation is done in finite volume. So this adds an additional layer of complication because you have to compute this in finite volume, and for that you have to use something which is called the finite volume form factor approach, which has been in particular developed very much by the group in Budapest around Gabor Takács. So there are lots of papers by them where they look at correlators of local fields in finite volume. So we needed to put these two things together. Why do we do this? So you might say, okay, you want to take volume to infinity at the end, so why don't you do everything in infinite volume from the start rather than doing finite volume? The reason is that if you try to do calculations in infinite volume from the start for excited states, you see that these sorts of functions here, infinite volume, they are plagued by singularities. So they're not very well defined. And so if you want, one way of making sense of their value is to compute them in finite volume first, and then use the volume as a regulator of those singularities, and then take the volume to infinity at the end. Okay, and that allows you to define this in a meaningful way. Okay, so that's a technical aspect. So a little more about these twist fields. So these twist fields are symmetry fields, so they are associated to a symmetry. And the symmetry that emerges in these theories is replica symmetry. It means that you start with your free boson, let's say, and you take n copies of this free boson, n non-interacting copies. By doing that, you now have a theory that has a very big symmetry. In particular, it has permutation symmetry among the copies. And associated to that symmetry, you have a field, this twist field, which is semi-local with respect to other fields in the theory. So if this is a field living in copy I, when it goes around the twist field, it goes to the copy above. Okay? If it goes around in correct order, in the correct way. So you have that field expressing that symmetry. And one way to, okay, and in general, when you have twist fields associated to any symmetry in QFT, one way they are represented is as fields that sit at the origin of branch cuts in space-time. Okay, so what happens to these twist fields, if you think about the finite volume geometry we're thinking about here, you have your time, which is infinite, you have finite volume, so everything is compactified on a cylinder. you have these two twist fields in there. And then, to compute their two-point function, ideally what you want is to introduce a sum of a complete set of states in the middle. So you want to do a trick such as this. So you want to reduce your problem to computing these so-called form factors of one of those fields. But if you want to be able to implement that operation, somehow you have to make sense of this infinitely long branch cut. In finite volume, that is complicated, because the branch cut will wind around the volume. So one trick to deal with that is to use the fact that this branch cut can be deformed as you like in QFT. So you can deform it in the time direction, and so allow it to be infinitely long. And then once you have that, you can make sense of these individual matrix elements in there. Okay, so this is one step, one technical step. Once you have done that, each of these matrix elements, you can represent it as an object like this. And because you're computing things in finite volume, the aspect that is technically tricky when you do the calculation is that you have this state, which was your excited state, okay? And you have that intermediate state in there. And because there is a branch cut in here, and because there is finite volume, the momenta of the particles in those states will be quantized. And the way in which they are discretized, or they are quantized, really depends on the presence of this branch cut in here. And because this is a branch point twist field, which is rather non-trivial, this quantization condition is relatively complicated. And this is the part of the calculation that's kind of more complex. And that's why we did free theories and not more general ones. So I'm aware I'm going over time. So let me just show you one last technical slide. So one idea that we used, which some of you might have heard of, is something called the Dublin trick. This is a proposal that was made by Samologikov and Fonseca a few years ago, and they used this idea to do calculations in the Ising field theory. And this Dublin trick is the idea that if you have a free fermion, let's say, or a free boson, and instead of considering that, you consider two copies of it, what you do is you introduce an additional symmetry, a U1 symmetry in the theory. And associated to that, you also have a twist field, a U1 twist field. And it turns out that if you do this in addition in our replica and copy model, you now have the replica and you also have the doubling. So you have twice two operations, relatively complicated. But the advantage of that is that if you use that trick, you can essentially diagonalize the action of these twist fields in terms of these U1 fields that are simpler. So these U1 fields, they act like this. They don't change copy. They just add a phase. Okay. So what is the upshot of all of this? Is that all of these correlation functions I was trying to compute and matrix elements, you can rewrite them in a new basis of creation and annihilation operators where the action of that twist field is diagonalized and everything can be computed rather easily. And the fact that this can be done has a little bit to do with the theories being free. The fact that this Dublin trick makes everything so simple. So once you have gone to these new U1 fields, the quantization conditions of the momenta, they become something like that. So in the original state, they have to be just integers. And in the state here, the intermediate state, they are integers plus some phases that come from the presence of those twist fields in there. Okay. Now, when you put all of that together, and and you replicate and you do everything, let me pass this fast, you realize two things. One is that you get naturally a 1 over L expansion of this correlation function. And the second thing you realize is that the leading term on that expansion is of order 0 in the volume. So there is a constant term. This is the one we are looking at. Okay, so we get something non-trivial. And that constant term not only goes like L to the 0, but is proportional to the vacuum two-point function, which is very nice because we wanted to divide by it in my original formula. So that comes out, it factorizes. And what remains is something, for example, like this. This is just an example to show you how it looks for a one-particle excitation. So this is a one-particle excited state in there. You look at that ratio and you find things such as this, which in the end simplify to this, okay? And what are these things? Well, these C's in there, these are coefficients that characterize the state written in this special basis where the twist field acts diagonally, okay? And these G's are some functions of this variable R. And these functions are very, very important, okay? They turn out to have two expressions like this. And they emerge naturally in this computation. They emerge naturally by looking at the behavior of the matrix elements of these fields near kinematic poles, near their singularities. It turns out that they behave like this, and it's by multiplying many of these functions together that you eventually get the correct R dependence of the whole calculation. Okay, so let me conclude just by telling you that, okay, we have presented a set of QFT techniques to compute the entanglement difference between excited state and ground state in free theories. Some of the formula had been shown to work in a semi-classical approximation in numerical work, but this is an analytical derivation in QFT, which is pretty nice. It incorporates also the effect of indistinguishability of particles, so it is a difference whether you have bosons or fermions. And the formula seemed to hold in a large variety of situations in the QFT regime, in the non-universal regime, even in higher dimensions, which is rather nice. Let me tell you something about what we could do next. Something that is natural for us is to look at interacting theories in 1D, and we are pretty confident that at least for integrable models the results will be the same. And there are many reasons to think that. There is no particle production in integrable models, so this qubit interpretation seems to be natural still. From a technical point of view, in this calculation I presented so fast, the only thing that mattered was the pole structure of the form factors, and that is the same also, even if you have interaction. So we think everything will follow through, but we have to adapt this doubling trick to deal with interaction, and that's the kind of technical sticking point. The results also, I mean, in spin chains, actually, in the work of Vincenzo that was also studied, it's actually easy to see that if you take like an XXZ spin chain and you take a one-particle state or a two-particle state where there is a scattering matrix that is non-trivial, these states here represent all spins down and 2 up, or all spins down and 1 up. For these states, you can by hand do the calculation and see that we get our formulae as well. So, I mean, they emerge certainly in interacting QFT theory, spin chain theories. So that's also support that they should hold more widely. And this kind of states can emerge even in non-integrable spin chains. So we think that this even goes beyond integrability. If there is particle production, then there's something to think about, because if you have excitations and they can interact to produce other particles, then perhaps that spoils the results. Well, we have to think about it a bit. But if there's just one particle, for example, one excitation, then everything should follow through, I think, quite generally, even with interacting theories. The one-over-L corrections are interesting. We'd like to look at those still a bit more. And let me conclude just by thanking EPSRC for funding us. And this is the end. Thank you.
Thank you very much, Olalla. So we had already some questions during the talk, so but if there is some urgent question,
about one of your last generalizations, what if I considered a one-particle state that's not a momentum eigenstate but has some wave function? Then, I mean, you know, intuitively you would expect that you would again get, you know, basically it would be a qubit with, you know, just according to the fraction of the wave function that's inside and outside of the two regions.
Okay.
Does that seem like a doable calculation? I mean, in other words, did the fact that it was a momentum eigenstate, was that really actually important in your calculation?
I mean, it is important to some extent. I mean, for the analytic calculation in QFT, you use that structure, but I don't think it's fundamental. I mean, so I think it should be possible to do the case that you are describing, and perhaps results would be similar. I mean, I don't see why not. I mean, it seems that very plausible. It should be very similar. Yeah, but I haven't done it, but I don't see why not. Yeah. Other things? Okay. Thanks.
Other questions? Okay. Well, thank you, Olalla.
Thank you.